I'd like to introduce Damian Alvarez from Jülich Supercomputing Centre to talk more about Jupyter.
All right, then, yeah, let's get it started then. I'll try to keep it a little bit dynamic, but I know that after lunch is always a challenge to stay focused. So I'll give my best, but yeah, I mean, at the end of the day, it's a relatively technical presentation, so I'm not sure how well that's going to work. Anyway, so yeah, starting Jupyter. I don't know. Maybe I'll take example of one colleague that presented before. A small poll before we start. Who knows or who has heard about Jupyter? Nobody else has heard about Jupyter? I know Thomas has heard about Jupyter. Okay. Okay. Well, then let's get it started. So. Just for those of you that don't know, Jupyter is the name of the next supercomputer that we're going to deploy in Jülich, and it's scheduled to be the first exascale system in Europe. All right. So yeah, before we look at the future of what is coming, let's maybe take a look at a little bit at the past. So think about different previous epochs in supercomputing. We had the terascale era and the petascale and now exascale, and these were the years and the countries or regions that were hosting these systems. So maybe just as a, let's say, a short overview, probably lots of you know this already, but for terascale, the United States came first, and then Europe a few years later. For petascale, the same trend happened. For exascale, we see a huge change already. So China came and took over the rest of the world on this race, and Europe is still scheduled to reach this epoch a few years after the one that break the ground here. The takeaway for that for me is that we've been saying in Europe for a long time that we need to prioritize these kind of things more and invest on them more, and that kind of reflects that we are not really at the tip compared to other areas, but we are also not falling behind. So that's already, I think, a good takeaway. Yeah, so I'm taking a look at the systems that broke exascale already. We had the first one in China. We had the second one in the US, and then, Jupyter, that's going to be the first NVIDIA-based exascale system in the world for public research. Of course, I'm not counting here, the big systems that Meta or Microsoft or all these hyperscalers are deploying, that I'm not putting that into the equation. Right. So how do we get here? The road to exascale in Europe started already quite a few years ago. The first time I've heard personally about exascale in Europe was about in 2011, when the first European-funded projects started for focus on exascale. There were the Deep project, Mont Blanc, and Cresta. And the product of those projects is actually, you can see it clearly reflected on Jupyter, even though they started already so long ago. Mont Blanc was the first project, as far as I know, that advocated ARM for HPC. Is this coupling too much? No? Okay. And within the same funding round, we had Cresta and Deep as well. Deep was led by Jülich, betting on what we call the modular supercomputing architecture. And so these are things that you can see on Jupyter today. Then there were a few years where, with this, they are blank there because not because nothing happened, but because the same pace kept happening on the background. There were new projects funded focused on exascale. And then about 2015, there was started a discussion about having infrastructure funded and deployed in the EU. That's what the discussion that at the end brought up EuroHPC. And so, within the, let's say, the framework of EuroHPC, then there were a few years later, the first pre-Exascale systems that were deployed within this framework, and well, also the call for expression of interest for hosting entities, and well, all these pre-steps that took to 2024 this year to deploy Jupyter. Right, so maybe a couple of words about our road as Jülich to become a hosting entity for this system that, as I mentioned, is funded partly by EuroHPC, which is relatively new. So we started in 2021. There was the call for expression of interest. So basically, for supercomputing sites, they would raise their hand and say, "We are up for hosting this system." Well, then a little bit later, not too much later, was the deadline for applications on Valentine's Day. And then, well, there were a few months later the hearings, and then in June the decision. So the timeline was relatively compressed. And in June, I think it was in time. No, it was a little bit after ISC, or maybe during ISC. I'm not quite remember. Sorry. So well, the decision was taken, and then Jülich was selected as a site for hosting Jupyter. And that's when, let's say, our journey in Jülich started to prepare for launch. We are in Earth. We want to reach Jupyter, and so we started having the preparations for what do we need as a system, how are we going to evaluate the different tenders, things like that. I'm focusing also on these four, let's say, areas or challenges for the system. I'll touch a little bit on that later. Right, so I started our journey. We published the call with a descriptive document. That was a document for vendors to say, hey, we want a system with this and these characteristics. So if you think you can provide it, then make a proposal. Then, well, that was the deadline for the request for participation, the first round of evaluation, notification, and then the first dialogue. What this means here is that this was not a tender where we directly gave to one or another. There was a competitive dialogue. So we had 2 rounds of dialogue with all the vendors that wanted to participate to refine what we actually wanted, to refine what they could propose, to see if there's some friction points that could make sense or that could make the project not be as great as it could be. So, well, we had these 2 rounds, and then the final invitation to tender after these 2 rounds of dialogue. Yeah, so in June was the invitation to tender, and just 1 month later was the deadline for final tender. What this means for the vendors is that they had to prepare their commitments for the benchmark, what they promised they would achieve in a very compressed amount of time. But a compressed amount of time is a general topic on the project, so to say. So these were the benchmarks that we initially wanted to have as part of the evaluation. Then after the dialogue phase, couple of those flew out, and we structured them on. We want us to focus on the GPU side. We would have, or Jupyter is going to have, mainly think about compute 2 separate models. One focus on GPUs, one focus more on a general architecture, so to say. And so we structured the benchmark suite in this way. Right. So, well, then after that, the vendors suffer quite a bit to deliver all that needed to deliver on this month. All of them said the amount of benchmarks and the amount of time is too much, but they all made it, so it means that it was also doable. And then, well, we had the evaluation of the best and final offers that they made. Right. Well, and then so after that there was a series of meetings to decide who's gonna win the tender. Right. Good. And so at this point, then the contract negotiations started, and they eventually in October the contract was signed. Right, so the first challenge for us about Jupiter is what we call Optimus Maximus. Optimus Maximus was the place where Jupiter, the god, was living. So it was a temple that looked something like this. Somebody did that on Minecraft, but it was something like that. And what this means for us, this is for us a modular data center. Our current data center is big, it's relatively big, but the requirements for Jupiter are just too big for our data center. So we need a new one. There were a few years of discussions on how we should do that, and then at the end, well, the decision also for, let's say, for timeline requirements, etc., was that we will go for a modular data center approach. Yeah, so that's basically it. So this is the campus of the research center. I don't know if you guys heard before about Jülich, but it's a big research center, multidisciplinary, 6,000-7,000 people. The supercomputing center is just a part of it, which is there close to the lake. And so zooming in, this is where our two main buildings are at the moment, 16.4, 16.3, and then just to see the scale of what is going to be the new data center, you have it there on the northwest side. Right. So, well, at this point, lots of the design decisions for the data center have been taken already, and basically we are on preparation for start deploying basically the containers that are going to host the system. Right. Yeah, okay, so this is basically what I already mentioned, so I'm not going to spend time on that. We have a couple of pre-renders of how it will look like. Those are pre-renders. It has changed already. There's a couple of details that have changed already, but you have you can have the general idea of having, well, a few rows where we have the water-cooled racks. That's what you see on this side here. I think I can point, right? Yeah. So over there, those are the what we call the Sequana racks. Sequana is the architecture of Atos, which is a company, Evidence, sorry, the company that won the contract. And here you have, well, the other equipment for storage, admin infrastructure, logging nodes, etc. And this is basically all the electrical infrastructure. Good. So that's where Jupiter is going to live, and that's really the first challenge, because at the moment the building is not there. This is how it looks like now. This is a picture, I think, from last week. So at least the preparation work for laying out the containers is mostly finished. So from that point of view, everything is fine, and we're good on track. Right. Then let's take a look, maybe a little bit more technical details about the system itself. Well, just here a few let's say, general points. Our target is to reach 1 exaflop of delivered performance, not peak, but actually delivered on Limpac. That means, with the architecture, with the chips that we have, that means about 93 exaflops for AI for reduced precision. And to achieve that, we will get roughly 24,000 Grasshopper nodes. Not nodes, sorry, Grasshopper modules, and about the node structure we'll see in a second. Right, and the target is to have that as well in a power envelope of about 18.2 megawatts during operation. It could be peak, could be a little bit more, but the usual production should be around that. Okay, to understand a little bit better how Jupiter looks like, we have to take a look at what was our approach over the years in Jülich. So in Jülich, we had this dual strategy, where on one hand, you have the more general purpose clusters of more for let's say, day-to-day calculations in a way. And then you have the highly scalable for what we could call the hero runs, right? And so we had these two set of systems for a very, very long time. And already with Jubels, which is, well, actually already with Eureka at this point, we started merging both approaches. And with Jubels is our current flagship. also has these two parts integrated. And so following this idea, or following this approach, is what we have for Jupyter as well. So Jupyter has basically all these modules. Some of them are not there, but they are something that could be integrated in the future. But the ones in blue are the ones that are definitely going to be there almost from the beginning. So, and also the ones that you see that are closed in highlighted in red, those are the ones that were part of the procurement for Jupyter. And I'm saying that because this part of the storage, that is something that we are contributing in kind. So that was not part of the procurement, that was a separate procurement. So that is also adds up to the challenge, so to say. We are integrating not just system, but we're integrating procurements and orchestrating procurements to get everything working properly at the right time. So what you see here basically is, well, this is the main part, and this is what is going to get to the exaflop, and that's where the focus is. And then we have what we call a universal cluster where the nodes are not accelerated, and we have, well, some flash-based storage and the more, let's say, traditional storage with the spinning disks that I just mentioned. Okay, so zooming in a little bit on how the nodes, or to take a look at how the nodes look like. This is an actual blade for Jupyter, and each blade has 2 nodes. Each one of these two nodes has 4 Grasshopper modules. A Grasshopper module, in case there's somebody that doesn't know, it's basically one Grace CPU, ARM-based, and one Hopper GPU, and they come in a single board, in a single package, and so what? So basically, we're going to have 8 of them per blade. Each node would have, similar to what we already have in our current system, we have the same number of NICs or HCAs than the GPUs, and in total we have about 5,900 compute nodes to reach this exaflop. I'm saying about this, there is a number, but it needs to be proved. Our target is the exaflop, so if with the number we have in mind we don't reach the exaflop, then we're going to get a few more nodes. But it should be around this number. I don't see the pointer. Yeah. It should be around this number of nodes. Right. As I mentioned, it's going to be in Sequana racks, and they're directly water-cooled, very, very dense, which also allows to deploy such a monster of a system, so to say, in a relatively limited amount of square feet. Right, so I think that's everything I wanted to mention here. And just to compare it with similar systems that we can see in other HPC centers. So here we have the systems that we have at JSC, so Jupyter, what it's going to come. But it's what we have now. And this is more or less the node architecture, and similarly to what you can see in Oak Ridge for Frontier or Aurora in Argonne. So you can compare them here just to get an idea that if you want to reach to these compute levels, I think everyone, I think we all agree that you need to go via the accelerated way. Right. And then we have the other part of the system, more targeted towards users that are not in a position to benefit from GPUs, at least not now. And so this is the technology that we intend to deploy for this part of the system. Basically, per blade, we're going to have 3 nodes. Each one of these nodes dual CPU and based on SidePad, also ARM processors. Right. Then moving on the other modules of the system, the Scratch or the Flash partition is going to have 20 of these nodes. IIIS 6000 from IBM. It's based on GPFS. So we've been using GPFS for a long time in Jülich. it's not a hard requirement, but it's something we're familiar and comfortable with. So yeah, I think that's basically everything that it's important to mention here. There is, well, the network technology, it has a little bit of difference with what you can see in other parts of the system, but that we'll cover in a couple of minutes. Now, something that is also special here as compared to the storage that we used to have on Jülich until now is that this is going to be exclusive for Jupyter, meaning it's integrated on the InfiniBand fabric. And for lots of sites, it has been always like that. For us, we typically have a storage cluster that serves all the different supercomputers we have, which means that the storage cluster was in an Ethernet fabric, and we needed to bridge that. And this is not going to be the case in Jupyter. Right. Then for the high capacity storage, we have basically the same technology from IBM, but instead of having flash disks, we do have JBODs with the spinning disks to reach the capacity that we need. Right. So I think there's nothing. Well, maybe just mentioning the total capacity that is going to be about 300 petabytes gross. Good. Let's take a look at the time. The network of the system, the network design, is, as I already mentioned, is based on InfiniBand. The topology is Dragonfly Plus. And of that, I think I'm just going to go over the next slide where it's a little bit easier to see. So we have, actually it's the one after. Let me go to this, and then let's go back to the other one. So Dragonfly Plus, and you see just taking a look at the Dragonfly groups, you see how predominant or how important, how heavy is the what we call the booster partition, or the GPU nodes. We have 25 Dragonfly groups just for GPUs, and then we have one for the CPU module and one for everything else, meaning storage and other admin areas. Now, coming back to the slide that I just had here, here you can see more or less the size and the chaos of this of the fabric. We do have a lot of endpoints. I think it was something about 50,000 endpoints. It's almost 900 switches, so it's a massive fabric, and it's going to be a challenge to manage it. But it's at the same time it's not that far off from what we already have in Jubels. It's just maybe a couple of hundred switches more, but it's not orders of magnitude more. So we are relatively confident that this is doable. And one interesting thing is that here in the middle, you see that this blue area is because of these links, meaning in the core of the system we have NDR 400, but on the edges, so connecting switches with nodes, we have NDR 200. Right. So I think that's everything that makes sense to explain here. Then zooming in into the Dragonfly groups, this is basically what it is inside each one of them. We have a factory topology inside them, with 16 switches at the L2 level that are connecting to other L2 switches and the other Dragonfly groups, and then basically all-to-all with L2 and L1 switches. We have one switch less at the L1 level because basically that was the right balance for this design. Good. And here you can also see what I was mentioning, that NDR at this level and everything on top, and NDR 200 between nodes and switches. Good. For the CPU-based partition, it looks a little bit different. At the end, we have the same bandwidth going into the Dragonfly Plus, but the number of switches and the ratio between switches and L1 and L2 switches is slightly different, but basically, yeah. So we have 32 switches L2 as opposed to 16, but the number of uplinks is slightly different. But thinking about the Dragonfly group, so to say, it's, you have the same bandwidth going into the Dragonfly Plus. Good. And then the admin network, or the admin cell, sorry, the topology here is still not 100% decided, so that's why you have all naively concentrated on those switches. That is, of course, not going to be the final design, but there's the final design for this part of the topology still needs to be done. But what is interesting here is that the flash nodes are going to have NDR instead of NDR 200. So those are the only nodes in the whole system that are going to have NDR 400 directly coming out of the node. Okay, yeah, so this is just a summary of all the different kind of nodes that we're going to have here. Good. So, well, to orchestrate this, and without going too much into the depth here, we will rely on the SMC Exascale software stack. That is the stack that everything uses to manage their supercomputers. That is also a departure from what we use until now. What we used until now was kind of a homegrown software stack. For Jupyter, we intend to use their software stack, and well, we are in a phase of deploying that already in a test system. We already have a rack with a few of these blades and a small version of the admin island, and so we started already testing this. Right at the same time, for resource management, MPI, and health checking, we will rely on the software provided by Patek, which is another actor in this project. Actually, the consortium that proposed the system was not just Evident, was Evident and Patek. Yeah, so that's I think that's basically it. So we rely on Ansible. The system will use Slurm, and our software stack will rely heavily on EasyBuild. Good. I think, yeah, just to kind of end the talk, we have a program. So if any of you is interested on running on this system, and you're coming from let's say from the application corner of HPC, we have what we call URIP for Jupyter Research and Early Access Program. It's basically, as the name said, an early access program. So people that are applying to it, if the proposal gets approved, they will get early access on the system when it's start being deployed, but also on the test system that it's been deployed right now. So just as a preparation to make sure that once the system starts running, that everyone is up to speed and can be productive from day one. We use the same structure for Jubels as well. When we deployed Jubels back in 2020, Jubels Booster, that worked quite well, and so we are doing something similar this time as well. So if you yourself are not, let's say, coming from an application corner, then tell your colleagues that are coming from applications that they should be looking into this if they are interested on running on the first Exascale system in Europe. And I think that was all. So,
all right.
If there's any question?
Thank you, Damian.